Hey kids, welcome to section 2.6, transformations of functions. Today we're going to learn to identify the effects on the graphs of functions by replacing f of x with f of x plus k or f of x minus h for positive and negative values. And then what we do also when we put values in front, multiply a times f of x or f of ax, things like that. So you may have realized last section when we talked about absolute value functions that sometimes we are moving things right and left and sometimes we are moving things up and down. And so we're going to talk specifically about that movement today that we started talking about in the last section. So in a family of graphs, which have at least one common characteristic, the parent graph is the graph of the parent function, the simplest function of the family. Basically, the absolute values that we talked about in the last section, that's the parent function. It's the most basic absolute value function. But if I then draw another one over here, I've now transformed this first one into something else by translating it right and translating it down. And so when we talk about translations, we're talking about taking a graph and moving it side to side or moving it up and down to get a new picture. Transformations, there are other transformations, and you guys talked about these in geometry class. Dilations, rotations, translations, and reflections. So the first one we're talking about, like I said, is a translation. We're moving it side to side and up and down. When a constant k, so we're going to call that number that we're moving it, the number of spaces, a k. When a constant k is added to or subtracted from a parent function, the result is f of x plus or minus k, and it's a translation up or down. So when that k is put on the outside of the function, that's a shift up and down. When the constant h is added to or subtracted from x before evaluating a parent function, the result, f of x plus or minus h, is a translation right or left. And notice that if it's a plus k, you are translating left. If it is a minus k, you are translating right. If the plus k is on the outside, then, oh, my bad, these are supposed to be h's. There we go. H's and k's. H's are being added or subtracted from the x, and k's are being added or subtracted from the y's, or in this case, f of x's. So as long as you can remember that the inside is right and left, the outside is up and down, it helps you graph functions quicker. So describe the translation in each function as it relates to its parent graph. Then graph the function. So kids, look at letter A, y equals absolute value x plus 3. The parent function is going to be this function right here with all the pluses and minuses taken away from the problem. So the parent function is y equals absolute value x. You take away any plus or minus or multiplied numbers. That's called the parent function. If you look at letter B, your parent function, if you strip away everything, y equals x squared minus 4, the parent function is x squared. If you look at letter C, y equals absolute value x minus 3, and then plus 3, take away all the pluses and minuses, and the parent function is absolute value x. So the parent function is just the stripped down version of the graph. Now, this plus 3 inside means you're going to go left 3. So we're going to put translate 3 left. Okay, so that plus 3 means translate 3 left. So if your normal graph is going through 0, 0, then you're going to go 3 to the left, and that's where your graph is going to go this time. So instead of it going through 0, 0, we're going to go 3 to the left, and that's where it's going to go. Now the normal graph we learned in the last section is looks like this. And so normally it's just right one, up, or up one, right one, up one, right one. So you're going to put some more dots in here so that you can draw the graph. If you want to, you can make a completely different XY table if you want. But the point is that that +3 there is taking the normal graph and shifting it 3 to the left. So you don't actually have to make a whole table for it. If you know what the parent function looks like, then you can just shift everything 3 to the left. Letter B, y equals x squared minus 4. So the parent function is the parabola y equals x squared. This minus 4 means we're going to translate down 4, or translate 4 down. So a normal parabola is going to be an opening U that goes through 0, 0. This time ours is going to go 4 down, so instead of 0, 0, it's going to go at 0, -4. And the normal XY table for a parabola from -2 to 2 is going to be 4, 1, 0, 1, 4. So the first dots go out 1 and up 1, but then you go out 2 and you go up 4. Again, if you have no clue what's going on, you can always just make an XY table and graph it. Not this XY table though, because that's for the parent function. I'll show you how to do it in this one. So letter C, y equals absolute value x minus 3 plus 3. Strip away everything. Your parent function is absolute value x. This minus 3 inside is saying to translate 3 to the right. 3 right. And the plus 3 on the outside is 3 up. So if you want to, you can just make a table for this. So if you plug in -2 minus 3 is -8, absolute value is 8 plus 3 is 11. You can also put this on your graph. You can graph it on your calculator and then just transfer it over. So this gives you 7, and this gives you, no, that's not 11, that's 8. That's why. This is 8. Plug in 0, you get 6, and then 5, and then 4. So -2, 8's up here. -1, 7, 0, 6, 1, 5, 2, 4. Well, we haven't really bounced back up yet. So if we plug in 3, we get 3. If we plug in 4, we get 4. Oh, there we go, bounce back up again. All right, so important thing to remember is if it's on the inside of the absolute values or the functions, then it's right and left. If it's outside, it's up and down. If you're doing a parabola, you would have the plus and the minus inside of the parentheses before you squared it. We'll see more examples. Okay, second type of transformation we're going to talk about is a reflection. A reflection is going to flip the figure in a line called the line of reflection. Now, we're only going to deal with 2 basic ones in class this year. We're only going to deal with reflecting over the x-axis or reflecting over the y-axis. So remember, if you have a coordinate plane, this is your x-axis here, and this is your y-axis here. So if you're flipping something over the x-axis, you're taking it from above the x-axis to the bottom of the x-axis. So you're going to reflect it bottom to top or top to bottom. If you're reflecting something over the y-axis, you're taking something from the right side of the y-axis and putting it on the left side of the y-axis. So you're flipping from left to right. Notice that depending on which axis, your negative is either going to be outside of the function or inside of the function. So if we're reflecting over the x-axis, your negative is on the outside of the function. If you're reflecting over the y-axis, it's on the inside. So Let's take a look at some of these. Describe the reflection in each function as it relates to its parent graph, then graph the function. So letter A, y equals negative absolute value x plus 3. Well, the parent function is going to be absolute value x. That negative means we're going to reflect it over the x-axis. Reflect over x-axis. And then the plus 3 on the inside means we're going to translate 3 to the left. Translate 3 left. So now we have to graph it. So we can make an XY table. So if you plug in -2 plus 3 is 1, attach the negative, plug in -1, you get a -2, plug in 0, you get a -3, plug in 1, you get -4, plug in 2, you get -5. So if we do this, 0, -3, 1, 2, yep, it's going to keep going like this. We need it to bounce back down over here because that negative tells me it's going to reflect back. So that means I need to go the other way and I need to plug in -3. If I plug in -3, I get 0, okay. If I plug in -4, I'm going to get -4 plus 3 is -1. I get -1. Look at that. There's our starting to bounce back down. So once we know what the picture is going to be, once I know it's reflected over the x-axis, so it's going to reflect down and it's going to translate left, that's going to also help me draw my picture because I knew it had to keep going to the left. All right, letter B, y equals -x squared. Our parent function is going to be y equals x squared. And the negative means we're going to reflect over the x-axis. So I can make a table. -2, -1, 0, 1, and 2. Now if I know what the basic parabola looks like, all I need to do is take that upward facing u and reflect it to a downward facing u. But if you don't know what the ordered pairs are to make up a regular u, then just plug and chug. This negative hangs out on the outside until after you've squared the x. So if you square -2, you get a +4. Attach the negative for -4. Square -1 to get +1. Attach a negative to get -1. Plug in 0, you get 0. Plug in 1, you get -1. Plug in 2, you get -4. So -2, -4, and it's going to be a parabola, which means it's a U-shaped. So you also should be getting more familiar with, if it looks like a squared, it's a U. If it has absolute values, it's a V. And now you're going to connect these. All right, letter C, y equals absolute value -x plus 3. Well, the parent function is going to be absolute value x, so the picture is a V. The negative on the inside means to reflect over the y-axis. And the +3 on the outside means translate 3 up. So we're going to have a V that opens upward that has been shifted upward and is reflected over the y-axis. So let's make a table, make sure we get that. -2, -1, 0, 1, and 2. This time when we plug in -2, we're going to make it positive before we absolute value it to become +2. +3 gives me 5. Plug in -1, you get 4. Plug in 0, you get 3. Plug in 1, you get 4. Plug in 2, and you get 5. Well, I see some repeating there in the y, so that's good. It means we might not have to extend it. -2, 5. -1, 4. 0, 3. 1, 4, 2, 5. Well, there's my V. Now it says it's reflected over the y-axis. Keep in mind that if it's on the y-axis, then flipping it over the y-axis is just going to make the sides be the exact same thing again. So it's not really going to change much. All right, so the first transformation that we did was a translation. Second one was a reflection. Third one we're going to do, third and final, is called a dilation. The dilation is a transformation where you alter the size of a figure but not its shape. So that means you might have a small triangle and then a bigger triangle. And if I was perfect, those would be exactly the same shape, just one big and one small. So where you put the a value or the size factor of the getting bigger or getting smaller, where it goes, either outside or inside, depends on if you are stretching something horizontally or vertically. If the factor, the twice as big, 3 times as big, is inside being multiplied by the x value, that's going to be a horizontal dilation. So we're going to be stretching it side to side or smushing it side to side. If that a value is between 0 and 1, it is a stretch horizontally. If that a value is greater than 1, it's a compress horizontally. I know there's a lot of rules to remember. Vertical dilation. So that happens when the value is on the outside of the function and you're instead multiplying the whole thing, the y, by a. If that a value is greater than 1, you are stretching it vertically, so up and down. If that a value is between 0 and 1, you are compressing it vertically or smushing it. So let's see if we can do some examples with these. Describe the dilation in each function as it relates to its parent graph, then graph the function. Okay, letter A, y equals absolute value 1/3 x. Well, our parent function is going to be absolute value x. The 1/3 in front, so it's a 1/3 and it's inside. So if we look at the rules, the inside 1/3, well, the number 1/3 is between 0 and 1. So we have a stretch horizontally. So stretch horizontally by 1/3. That means we're going to take something that normally looks like this and we're going to smush it. And when we smush it, it's going to go out wider and it's going to get flatter. So just imagine. So let's make an XY table. -2, -1, 0, 1, and 2. If I plug in -2, I get 2/3. If I plug in -1, I get 1/3. If I plug in 0, I get 0. If I plug in 1, I get 1/3. 2, I get 2/3. Now those are some pretty ugly kind of looking numbers there, right? So I'm going to do 0, 0 here. Now if I went ahead one more and plugged in 3, I would get 1. And that's nice to graph. And if I went one more in the opposite direction, -3, I would get +1 again. That's a lot nicer to graph. 1, 2, 3, 1. Okay, so notice that this picture is the normal absolute value function, but it's kind of been smushed down a little and out. Okay, letter B, y equals 2x squared. Well, the parent function is going to be the parabola x squared. The 2 on the outside. So if we go back up here, we're on the outside. So here we're at vertical dilation. And my number is greater than 1. So we are a stretch vertically. Vertical or stretch vertically by 2. That means we're going to get twice as tall. So the normal parabola might look like this, but we're going to get twice as tall, so we're going to be super skinny when we get stretched taller. So we make an XY table. Okay, we plug in -2, square it gives you 4 times 2 is 8. Plug in -1, you get 2. Plug in 0 is 0, plug in 1 is 2, plug in 2 is 8. So we get this picture. So when you connect it, look how skinny it is. It's twice as tall, and it almost looks half as skinny. Okay, letter C, y equals -3 absolute value x. So our parent function is the absolute value function. The negative on the outside, if you remember, is a reflect over the x-axis. The 3 on the outside is just like the 2 was on the outside. That's a vertical stretch. By 3. So let's make an xy table and see if it's reflected and stretched. So -2, -1, 0, 1, and 2. If I plug in -2, absolute value is +2, times -3 is -6. Plug in -1, you get -3. Plug in 0, you get 0. 1 is -3, and 2 is -6. So, 2, 4, 6, 2, 3, 0, 0. Okay, so it's supposed to be a V. Yeah. And it's getting taller. And it's opening down. Awesome. Okay, last slide. So here we have some examples of befores and afters, and we're going to have to say what happened. So in example 4, we have 2 graphs here. Based on the graph, which equation can be used to describe g of x in terms of f of x? So they want you to describe how to get to g if you start at f. So we're going to start at f, and we want to finish at g. The most important thing is to look at like a focal point. So if you look in the f starts at 0, 0 at the vertex, and it moves over here to -3, 4. So it's moved 3 to the left and 4 up. 3 left and 4 up. So now come to the equations and figure out which one is 3 left and 4 up. Well, 3 left would be inside and opposite. So 3 left would have to be C or D. So it's not A or B. Because, for instance, A is right 3 and up 4. B is right 3 and down 4. C is left 3 and up 4. D is left 3 and down 4. So as you can see, you could also match it that way. Left 3 and up 4 is going to be C. All right, if you're looking at letter B, we're again trying to go from F to G. So it starts at 0, 0, ends at 2, 1. So that is right 2 and up 1. So let's look at the choices. Oh, and also it's reflected. Reflected over the x-axis. That means that there has to be a negative on the outside. So we definitely have reflection in A, and we have left 2 and up 1. Then we have a reflection with right 2 and up 1. We have no reflection with left 2 and up 1. No reflection with right 2 and up 1. So we definitely need a reflection. Right 2, up 1 looks like it's going to be letter B. All right, number 5, transform the given function f of x as described and write the resulting function g of x as an equation. Okay, so we're going to take f of x, which is the parent function for square roots, square root x, and we're going to reflect it across the x-axis, and we're going to translate it left 1 unit. Okay, well, reflecting something over the x-axis puts a negative in front of the whole entire thing. And translating left 1 is going to put a +1 inside. So g of x is the function we're supposed to be writing. Let's put the negative on the outside for the reflecting across the x-axis. Let's put the root x because that's the function that we're working with. Left 1 is going to be a +1 underneath the radical. And that's it. If I had any up or down, it would go on the outside. All right, letter B, f of x equals x squared. So this time we're working with a parabola, a quadratic. Translate right 2 and translate down 1 unit. Okay, so g of x, the function we're looking for. We're going to have a quantity squared for a parabola. If we're going right 2, that means we're subtracting 2 inside because it's always opposite what you think it is. And the down 1 is going to have a -1. All right, down here, example 6, describe the transformations necessary to transform the graph of f of x into that of g of x. So for letter A, we're going to compare f of x equals root x, and g of x equals negative root x plus 2 minus 3. And we need to figure out what's been done from f of x to get to g of x. So notice first there's a negative on the outside. A negative on the outside means to reflect over the x-axis. Make sure you tell me if it's x-axis or y-axis. The +2 on the inside means that you're going to translate 2 to the left. And the -3 on the outside means you're going to go 3 down. So reflect over the x-axis, translate 2 left and 3 down. Letter B, this time f of x equals x squared, so we're working with a quadratic. And g of x equals 2 times the quantity x minus 3 squared. So notice we have a 2 on the outside. A 2 on the outside is a vertical stretch. So we have a vertical stretch of 2. And the -3 on the inside is a translate 3 to the right. All right, kids, that is the end of section 2.6. If you have any questions, please let me know. And as always, keep calm and keep trucking.